I want to reiterate that what I spent last week doing with our BellWorks 2 full class days and BellWorks for about a week was how to solve problems using dimensional analysis. That was the main point. Everything else in this chapter, with the exception of percent error, really ties into this process of how do you solve a problem using dimensional analysis. And I got the impression strongly from the test that nobody quite caught that I was trying to teach you a procedure that will be usable on simple problems and usable on very difficult problems, okay? If you take this sheet that's on the screen up here, I've given you a copy of the steps. I thought it'd be available to you on the portal and everybody would look it up and print out a copy at home and then I wouldn't have to do this. But I have fit the 3-page document onto one single page. I expect you to know this and to use it by heart, okay? On the back are some sample problems, and the reason I showed you these sample problems, we'll do some of these problems this week, but there are some simple problems at the top that don't require you to manipulate the formulas much at all. The intermediate level problems do require you to manipulate the formulas a little bit. The advanced problems require you to manipulate the formula and do some unit conversions in the middle of the problem. And the challenging ones are just insane. And the reason I put them there, and I'm not going to solve them with you, is to show you that you could use this method to solve problems like that in the future if you decide to chase something you're dealing with flow, fluid dynamics, aerodynamics, aeronautics, anything that requires a little bit of advanced physics. You're going to find there is a lot more difficult types of problems. The procedure that I'm teaching you is designed to solve any problem, simple, intermediate, or difficult. It will work if you learn how to do it. So I'm going to re-show you how to do it. But when I look at your papers, and I know the time was short, but I gave you 20-minute warning, and by the time I hit 20 minutes warning on the test, that should have been your clue to drop everything else and start working on those problems. Okay? So we're going to work one of these nice simple ones here first. I've already done it at the end of the previous period. This was problem number 1 from the sheet that you're going to be doing homework problems from tonight. It's the same sheet we used last week, but I want to see every step listed. Okay, so the goal is to use these procedures to solve these problems. The first problem on that list was number 1. A ball is dropped from a cliff and reaches a speed of 29.4 meters per second after 3 seconds. What is the ball's average acceleration? Pretty simple problem. We're going to follow the steps. Step number 1 on your sheet says identify what variable we're looking for. What variable is being calculated? What is the variable that this is asking for? So right here, it's pretty clear. What is the ball's average acceleration? So the first thing you're always going to write down is the variable that stands for that acceleration. What variable, what letter of the alphabet represents acceleration? You're going to put an equal sign and the question mark because you don't know. This is what we're looking for. And then what units do we actually measure acceleration in? Now, everybody give me your eyes up here. I have given you, it's extremely tiny, I know that. I have a full-page document of these. I am assuming from previous classes that everybody in my honors classes knows everything in the lower right-hand corner here. Now, I'm going to just mention it. You can look at it with a magnifying glass in the future, tonight if you want. But you should all know that D stands for distance, V velocity, A acceleration, small t is time, capital F is force, M is mass, capital T is temperature, capital V is volume, rho is density, G is the acceleration due to gravity. These should sound very familiar. N number of moles, which may not sound familiar, but we will cover it in a month or two. Capital P is pressure or power, depending on whether we're talking about electricity or force. Momentum is small p, E is energy, like in kinetic energy or potential energy, and W is work. I know for a fact, almost with 1 or 2 exceptions, those are from your physical science class last year. Okay? I expect you to know that. So when I say we're looking for acceleration, everybody should know that's A. It's going to be A in some formula. Okay? The second thing that's on this list are a bunch of formulas. And again, many of these formulas down here in the lower right-hand corner, you should be familiar with. I am expecting everybody to have memorized what in the world is the velocity formula. Distance divided by time. What is the density formula? Rho equals m over volume, mass per unit volume, m over v. Acceleration should be something you know. It's final velocity minus initial velocity divided by final time minus initial time, or delta v over delta t, or you can just write it delta v over elapsed time. There's a bunch of different ways of writing it. It's on your sheet here. Newton's second law, force equals mass times acceleration. Pressure, force per unit area. Momentum, kinetic energy, potential energy. These should be extremely familiar to you, and I expect you to know them without me giving them to you. If you don't, again, make some flashcards and make sure you know them. Under units, okay, here's your base units: time, mass, distance, and temperature. It's measured in seconds, grams, meters, or Kelvin, or Celsius in some cases. And then your derived units as well: volume, density, velocity, acceleration due to gravity, and force. Okay, so these are some of the things that I'm assuming everybody knows already because you've seen them before in science classes. You had them last year in physical science, and I'm not going to reteach them to you. Okay, so when we need a formula for acceleration, in this case I gave it to you, but again on a test I'm not going to. Unless it's a formula I feel that you have never seen before or you're not familiar with because it was something that was not a major point in physical science last year. Change of velocity over time. Step number 2 says write down the formula that we are going to use. I don't want you to do anything to it yet because when I grade these I'm looking. What are we looking for? What do we know? Second step, what formula are they going to use? If this is wrong, you can't get the right answer, okay? So if you've chosen the wrong formula, or if you've got the formula memorized upside down, or for some reason you just don't have that one down yet, and you've written it down wrong, then there's no way you're going to get the right answer. And I can spot that right away, and I'll understand why you got the wrong answer, okay? The second half of step 2 says, if necessary, solve for the unknown variable. Now in this case, if it said, how much time would it take? Okay, now I've got to solve this for t. If it said, what is the final velocity? Now I've got to solve this for delta v. But in this case, I don't need to, because it's asking for its acceleration, and the formula says it's already solved for acceleration. Step number 3, substitute into the formula and solve. Use your calculator. So in this case, I'm going to take these numbers and put them into this formula. And I'm asking you to show me, literally, how they fit in there. 29.4 minus 0, parentheses, divided by 3.0 seconds. Grab your calculator, 29.4 divided by 3 is 9.8. Step number 4, label your answer, box it, make sure you have units, and check for sig figs. In this case, 3 sig figs and 2 sig figs mean my answer has to have 2 sig figs. Okay? This is what I'm looking for. This is what I expect you to be able to do. Every little detail. Okay? There is a lot that can go wrong here, but I want you to have this process down, like the back of your hand, so that when we get a month from now into PV equals nRT, or Boyle's law, or Charles' law, or Gay-Lussac's law, or the ideal gas law, those are the first ones I think that come up. You have a system for solving those things. Okay? Now, the second handout I gave you is this little form I made on Excel. It is a worksheet. Yay! Let's work a problem. I want everybody to take this out. I want you to fill in the little boxes with me, okay, as we do a problem. We're going to do number 2 right here. So I'm doing some of your homework problems with you in class, okay? It's okay. When you do it tonight, it'll be on a separate sheet of paper, nice and clear, working vertically down the page. Okay, problem number 2 says a car travels at an average speed of 30 meters per second for 0.8 hours. Find the total distance traveled, and I've given you the formula here. So we're going to use these steps to solve this problem, and I just want to make sure right now in class, because I'm going to walk the aisles, that everybody knows how to do this. So you're going to fill in these little boxes. I know it's a lot on here, but I'm getting you in the habit of working vertically down the page and writing the right things down. Okay, step number 1. What are we looking for? Somebody tell me.
Kilometers.
Okay, raise your hand, please. Okay, Drew.
Kilometers.
Okay, and what? That's a unit. I need to know what the variable is that we're looking for. Okay, we're looking for distance in kilometers. Distance, kilometers. So on your sheet, you're going to put a D, a small d, in the first box where it says variable. I've already given you the equal question mark. Okay, and then where it says units, you're going to put small k, small m, kilometer. We're looking for distance in kilometers. Now, I've indented, because every problem I solve for a week, I've done it this way. I wouldn't mark off if you didn't indent, but again, for me, it looks like, okay, here's what I'm looking for, here's what I know. It makes sense. Everything's organized. I can scan right down the page. I can see if you know how to solve this problem. If you didn't get the right answer, I can see if you punched it in the calculator wrong, or if you used the wrong variable, or if you didn't convert one of your units. So, under second variable, somebody else, raise their hand. What else can we list here as a variable? One of the variables for distance, velocity, and time. We already know we're looking for distance. What does this problem tell me that I know? Drew?
Little t for time, and then hours.
Okay, so maybe on the second line here, you're going to put small t equals, in the next box is 0.8, and then under units, HR for hours. What's the next variable that we know? Mr. Kennedy.
Velocity, the 30.
Okay, so next box, V equals, that's a small v. Okay, 30.0. Don't lose your sig figs because they're going to be important when we look at our answer in a few minutes. Whoops, it's not 30. Yes, it is. Never mind. Forgot I already scrolled it up. Okay, and in the units, meters per second. Now you can write that. Notice when I write it like this, that's so I can type it easily into a Word document. On your sheet, it might be meters per second. I like writing things this way when I solve problems so that I know what the numerator is and what the denominator is. This is the same as this, but it's going to be harder to see and harder to catch your errors if you're writing it this way. Okay, so I would encourage you to always have numerators and denominators for your units so that you can see what needs to cancel out. This is not always really obvious what needs to cancel out. Okay, let's go on. Second step, we're up to write the formula that we need to use. Now again, I've given it to you here. Everybody needs to know velocity equals distance divided by time. So on your sheet, you can put V equals D over T. Put it in there. V equals D over T, just like this. Don't do anything to it yet. I need to see that you got the right formula. Underneath that, it says rewrite the formula. So in this case, again, we're looking for distance. Who wants to solve this formula for distance for me, Kennedy?
Multiply both sides by t.
And you get
D equals v times.
D equals VT, or V times T, or T times V. D equals TV, or VT, your choice. But on that next line where it says rewrite the formula, if needed, we do need to in this case. So it's going to be D equals V times T. I assume everybody knows how to do this, but I know a few people are still struggling, but this one's not terribly difficult. I'm solving for D. I need D equals. So what Kennedy said is perfect. He said multiply both sides by T. T over 1 if you want to think of it that way. That's weird. That's my Bluetooth kicking in. Just shut him off. And on the right-hand side, we'll have the t's cancel out, and on this side now I have v times t. So d equals v times t. You can rewrite it. You don't need to show me that work as long as you know how to do it. you want to show me that work, that's fine. Okay, next step on our sheet, step number 3 here, matches step 3 here. Okay, substitute into the formula and solve. So now I'm going to take this velocity and this time, and as soon as I put those into the formula, you'll see I have a problem. Okay, so far. Let's skip down here. So number 1, we're looking for distance. We know velocity, we know time. We write the formula. We solve the formula for D. And when I get to the substitution step, I notice that my units are not going to cancel out. Now you can substitute them in. You have a choice. You can either put down here 30.0 meters per second and then try and multiply it by 0.8 hours. And you're going to say seconds and hours don't cancel out. You can either put a conversion factor in here next to it to change the seconds to hours or the hours to seconds, or you can do it up here. The way I've showed you so far is I like to usually do it up here. I'm going to change colors here. I'm going to change that hours into seconds by going 60 minutes per hour and 60 seconds per minute. That's going to be 3,600 times 0.8, which is 2,840. What did you got? 2880? Okay. 2880 seconds. Now that I have seconds, I know it's going to cancel out down here. So I can put that number here instead of the 0.8. 2,800 seconds. Something moved. How'd that happen? Whoa. Hey, let me rewrite that. Hang on. D equals 30.0 meters per second times 2,880 seconds equals. Okay. The units are going to cancel out. We're going to get the calculator out, multiply those two numbers. We're going to watch our sig figs. Here I have 3 sig figs, and here I have 1 sig fig. Okay? So my answer has limited to 1 sig fig when I finally get there. 30.0 times 2,880 equals 86,400. That's wrong up here, by the way. Is that kilometers? I believe that's right. This is in meters right now, okay? So this is in meters, not kilometers. And my sig figs are not correct yet. So I have one last step to do. We change this to kilometers by multiplying by 1 kilometer per 1,000 meters. And then we're going to change it to 1 sig fig, which instead of being 86.4 is actually going to round it off to 90. Okay? So my final answer down here, which I'm going to pull up here real quick, is 90 kilometers. It's 1 sig fig. My units match what I'm looking for, and everything is checkable. Questions? Good. Let me take a quick peek. How are we doing? Good. Good. I'll sit down there in a second. I like what I'm seeing. Thank you for bearing with me. Yay. Okay. Is there any general questions about the procedure? Okay. Let's do another one. The goal here is to do work problems so that we can see the different types of problems. This one, number one, step is very simple. There's no conversions. Everything's straightforward. I didn't need to change the formula. I didn't need to mess with the units. This one is really a type 3 problem, okay, down here, where if you read through that, we've got conversions to do, and we also had to manipulate our formula. We had to solve it for D in this case. So we had both things going on here. Okay, so let's try another problem here. Second, find one. Force is determined using Newton's second law, F equals ma, where force is in newtons, mass is in kilograms, and acceleration in meters per second squared. Use this formula to determine the acceleration. What are we looking for? Acceleration. Okay. So we're going to do another acceleration problem here. First thing I write down on the left-hand margin, if this is the side of my paper here, okay, always work down the page, please. Don't put stuff way over to the right unless it's a side scratch. You're just multiplying some numbers together or doing a quick conversion. I'm looking straight down the page. I'm looking down the page. Your work should flow down the page. Sometimes you'll only fit one problem on a page, 2 problems on a page, okay, or 3 problems on a page. Don't be afraid. If you finish the bottom of the page, flip it over, work on the back side of the piece of paper. If you fill that side, get a second piece of paper. Don't show me any, don't make columns on these. Guys, it's just a nightmare, okay? So, find the acceleration F, 182 newtons. Okay, so I know the units are meters per second squared for acceleration. They always will be. What in the world is 182 newtons? That gives me a number. I need to identify what that variable is. What is newtons a measure of? Hey, force. So what's the variable for force? Capital F, thank you. Okay, so I'm going to write F equals 182 newtons. Sometimes they tell you what the variable is with a word. You need to know what letter to use. Sometimes they just give you a number. You say, oh, newtons. What is newton? Oh, newtons is force. Okay? Newtons is force. So then we know capital F equals 182 newtons. The problem goes on. Calculate the acceleration F. 182 newtons is applied over an object with a mass of 0.146 kilograms. So in this case, they tell me mass. What's the variable for mass? Russell?
Kilograms?
Mass. What letter do I use for it?
G.
What letter stands for mass in a formula?
Gram.
No. True?
M.
M. Small m. Okay? Mass is m in every formula that I've ever seen it in. The problem with small m, guys, is it's also a meter. So m is a unit in meters. It's also a variable, mass. And that's very confusing. I can understand that for people that don't do this a lot. Okay? Especially for a 5th or 6th or 7th grader. Okay? But you've got to know, is this a variable, m stands for mass, or is it a unit? It's on this side, m stands for meters. mm stands for millimeters, which is a measure of distance, which is d. Okay, so, I mean, you just got to know, you got to use some common sense, everything's in context. M equals 0.156 kilograms. The units given in this particular case are kilograms. Okay, what's our formula going to be? Who remembers or you know it? formula for force, Newton's second law. Good.
Mass times acceleration.
Equals.
Force.
Okay, we've got to have an equal sign in here, okay? So F equals m times 8. Force equals mass times acceleration. Now, in this case, we're looking for acceleration. So now we have to do that step that says rewrite the formula. How would I rewrite that, Bert?
You divide by the sums.
And get what?
F or A equals F over M.
Say that again?
A equals F over M.
Yes, F over m. Divide both sides by the mass so that it cancels out on the right-hand side. Over here you have F divided by m, and this is the formula we need to use. Now, before we substitute, the next step is substitute. We'll see 182 newtons divided by 0.156 kilograms. The question is, are the units going to work out? Now, newtons are a derived unit, as are a lot of these, okay? And we need to know where a newton actually comes from, okay? So again, it goes back to this formula. The newton is actually a derived formula that comes from mass times acceleration. So I'm going to put a little box up here just to remind you guys. If 1 newton is a measure of force, and force is mass times acceleration, okay, then we should be able to remember that 1 newton equals mass, and this is in kilograms. This is the only tricky part. It is 1 kilogram times 1 meter per second squared. So by definition, 1 newton is the force required to move 1 kilogram 1 meter per second squared acceleration. Okay? You need to remember that. So I'm giving this to you. That's something that I probably would not expect you to remember, but I'm really reinforcing it right now. So I want you to remember. Okay? 1 newton equals 1 kilogram meter per second squared. And the reason that's important is when I look at these units, if I'm not careful, I'm going to write my units as newtons per kilogram, which is horrible. I'm not sure it would be wrong, but we can see if I rewrite this newton as a kilogram meter per second squared, that the kilograms cancel out, yay, leaving me meters per second squared. And that's what I'm looking for. So get the calculator out, 0.182 divided by 0.156. And then we'll go back and take a look at our sig figs. 182 divided by 0.156, 1166.66667. Let's pick on Michaela here for a second. How many sig figs here, Michaela?
3.
And how many here? So how many does my answer have to have? Good. Okay, so we're going to have 3 sig figs down here for our final answer. And it looks like 1166 is going to round to what? 1170, okay? 1170. Now I can leave it like that, or I can change it into scientific notation. Both would be correct. Or 1.17, don't include the 0, otherwise you'll have 4 sig figs, times 10 to the third meters per second squared. You don't have to give me both, one or the other. Okay? So it was 1167.66.66666667. Again, that's going to round to 3 sig figs, 117 or 1.17. Questions here? Does everybody see that what I'm expecting you to write, please? Okay. It shouldn't look foreign because I did it for a week. Let's do another one here. Power is a measure of energy per unit time, or P equals E over T. Power is measured in watts, energy is in joules, and time is in seconds. How many watts would be used for 5,000 joules to be used in 20 seconds? That's too easy. Let's do part B. If 150 watts is used for 21 minutes, how many joules of energy are expended? Let's do that one instead, okay? So how many joules? What are we looking for? Mr. Hopkinson?
Capital J.
Capital J is the unit. And that's a measure of what, Michael? Catch it here. Hey,
Energy.
energy, okay? So capital E for energy in this case. If it's kinetic energy, you can use capital K, capital E. If it's potential energy, you can use capital P, capital E. But in this case, it's just capital E. Because the formula that's given here, which I'll show you in a second, is P equals E over T. Okay, number 2, what do we know? The two problems, two numbers that are given here are, if I can find it, just lost it. If 50 watts, what's the abbreviation for watts? Anybody? Kenny?
W.
Yeah, if you ever bought white light bulbs or you ever looked at a light bulb, it tells you 50 W, 50 watts. That is a measure of what? What do we measure when we talk about watts?
Power.
Power. Good. You go buy a microwave oven, you're going to be looking at either a 700 watt or an 1100 watt microwave oven. They come in two different versions usually. If you go buy any electronic appliance, that's how much power. The more power something uses, the more electricity you're going to pay for to run that, okay? Refrigerators and heaters and air conditioners use lots of power. Little things like your phone run off of very, very low milliwatts for the most part. Okay. The second thing that's given here is 1 minute. And that would be a measure of small t or capital T?
Small t.
Small t. Make sure I see a cross on the small t. Remember, small t is times, capital T is temperature. That's just the convention that we use. Okay, the formula that's given, power equals energy per unit time. So we write down the formula. In this case, it's given to you. And that's one that you may have covered last year, but I'm not sure you spent a lot of time on it, so I'd probably give it to you, or you could ask for it if I didn't. And we're solving for E. Somebody solve this for E for me. Kennedy?
Almost like that too.
And you get
E equals PT.
equals PT. Whoops. Okay. Very similar to this one over here. Okay, we just multiply both sides by the denominator, and we get E equals P times T. Yeah, there's another thing we need to know. I don't know if you caught it here. This is like the last one. We need to know how watts and joules fit together. So I would give this to you if you didn't know it. Okay, by definition, 1 watt equals 1 joule per second. That's where we get watts from. It is the amount of energy. 1 joule of energy per second is 1 watt. That's a definition. And you kind of need to know that to work these units out. So down here, once we see the seconds over here, and the minutes here, we know we've got to do something about that before we substitute it into our equation. Tempe, how many seconds in a minute? Yeah. And again, the units tell you whether you're multiplying or dividing. Nobody should have to guess here. If I know there's 60 seconds in 1 minute, and I need the minutes to cancel out, then I'm going to be multiplying by 60. Those units are what drive this whole thing forward. And yes, I want you to show me. Say, Mr. Debski, can't I just write down 60 seconds? Because everybody knows 60 seconds is 1 minute. I want you to show me. I want you to show me the conversion. I had several people do that. You know that 3,600 seconds in an hour. I know that too, okay? But I want you to show me how you got that. Because sometimes it's not going to be so clear. I want you to show me. I did a unit conversion right here to change from seconds to minutes, or hours to seconds, or years to minutes. Okay, we can substitute now. E equals 50 watts multiplied by 60 seconds. And it's going to be 3,000, looks like. What are we going to do for sig figs on this? Al? Don't just leave it like that. We could. This one's a little bit tricky because once you do this conversion, you go from 1 to 2 sig figs. I'm going to kind of think of this as a whole number, as something that really is not significant. And I might be inclined to call this 2 sig figs and ignore this one, or call this 2 sig figs as well and put 2 down here. I'd be a little bit lenient on this type of problem because of this time right here. So whether you left it as 3,000 joules or 3.0 times 10 to the third, this would be 1 sig fig. This would be 2 sig figs. And in here, by the way, I didn't show this, joules per second. Seconds cancel out, so you don't have to show that as long as we know it. But if you don't know it or you want to show it, that's good too. 50 watts equals 50 joules per second times 60 seconds, and the seconds cancel out, giving us joules. What was the Bellwork question today? Let's see what we got. Let's do the Bellwork problem. What is how many grams? So we're looking for grams. Or what is the mass in grams of dextromorphan? Is that what it is? Dextromethorphan. I've heard that word, but I don't know what it is. How many grams are in 1 bottle? Now this kind of problem is similar but different in a couple different ways. Let's see what we need to figure out. Number 1, that's what I'm looking for. Number 2, what do I know? 1 bottle is 4 fluid ounces. I need to write that down somewhere. So I'm going to say 1 bottle equals 4 ounces. That's a conversion factor that I'm probably going to need in here. So I'm just going to list it here. Keep reading. It says for an adult, the standard dose is 2 teaspoons. 1 dose. TSP is the abbreviation for teaspoons, right? You may follow recipes. TSP for teaspoons, TBSP for tablespoons. How many teaspoons in a tablespoon? Two. Nope. Four. Nope. How many teaspoons in a tablespoon? Nope. It's 3. Anyways. You guys know your units. Or you don't do a lot of cooking. 3 teaspoons in a tablespoon. Here we go. Number 112. And a single dose contains 20 milligrams. These are all conversion factors. There's nothing here that's a constant yet. Conversion factor, conversion factor, conversion factor. Evidently we're going to need them. Let's keep reading. Using the relationships 1 ounce equals 29.6 milliliters. That's another conversion. And 1 teaspoon equals 5 milliliters. That's another conversion. I don't know if we're going to need all these or not. Find out. Determine how many grams are contained in a bottle. How many grams of dextromethorphan? Not grams of cough syrup. Standard dose is 2 teaspoons. Okay. Anybody want to start? Okay, I'm going to start with the whole bottle. Okay, where we want to know how many, what's the mass of dextromethorphan in grams in one bottle. So one bottle is right here. So I'm going to start with 4 ounces of syrup. Not dextromethorphan, 4 ounces of syrup. I'm going to call it SYR. Okay? That's a whole bottle, and that's what it's asking me. How many grams of this drug are in one bottle? I've got 2 minutes, so I'm going to go fast. What can I cancel out in this list that's in ounces with this ounces of syrup? Let's look at our list. That's no. Aha, what's that? Yeah, let's change it to milliliters. Okay, so I'm going to have ounces to 29.6 milliliters. So that's how many milliliters are in one bottle of cough syrup. Milliliters to tablespoons or teaspoons. Let's do that one next, because then I can go teaspoons to doses and doses to milligrams. I think we're getting there, okay? So let's go next to milliliters to teaspoons. 1 TSP, 5.0 milliliters. 1 teaspoon. Let's change it into doses. 2 teaspoons in 1 dose. And then lastly, we're going to change 1 dose has 20 milligrams of dextromethorphan. So over here, the dose goes in the denominator, and 20 milligrams, so 20.0 milligrams goes up here. Now, are we up? Have we answered the question yet? Give me 20 seconds here. Determine how many grams. So the last step is going to be change milligrams to grams. So we're going to need to do 1,000 milligrams and 1 gram. And if I take my calculator and multiply all those out, numerator 4 times 29.6 times 20 divided by 5 divided by 2 divided by 1,000. I should have the right answer. And you can double check it. We'll ask a question tomorrow. You guys are dismissed. Have a great night. I'll send a reminder out later today with those problems again, in case you can't find it from last week.